Okay, Zoomdall, Chapter 3, problem number 79. The purpose of this particular problem is to have you solve for empirical and molecular formula of Cumin, where Cumin is, well, we don't know the formula. We just know that if we take the Cumin that's made of carbon and hydrogen and we burn it, we get carbon dioxide and water. And the only information they've given us is the beginning mass of the Cumin, 47.6, and the final mass of the water that they collected after this burned. So really what we need to know to solve this problem is we need to know the mass of the carbon, and the mass of the hydrogen that's in this original Cumin. That's why we have these question marks here and here. So how can we do that? Well, the way we can do that is this. The mass of the hydrogen here, all of that mass of hydrogen had to come from the hydrogen here in our hydrocarbon. It's the only place it could have come from. And not particularly useful in this problem, but often in this kind of a problem, we could get the mass of the carbon in the compound if somehow we knew how much CO2 had originally reacted. So that's the solution we're going to take, is to find the mass of hydrogen and carbon in the original compound based on this mass of water. So here we have the equation written out again and the couple of pieces of information that are provided. And so in this first step right here, we're taking 42.8 milligrams of water. And we know from our molar mass of water that we've calculated down here, we know that in water there are 2.02 grams of hydrogen for every 16 grams of oxygen, or if you want to think of this total, 18.02 grams of water. So there are 2.02 grams of hydrogen for every 18.02 grams of water. Okay, so we've got that right here. We've got that. There's my highlighter again. We've got that fraction right here, and using that we get 4.77 milligrams of hydrogen in that original water. Oh, so now we're on a winning streak. We have the 4.77 milligrams of hydrogen, and we know that from this original 47.6 milligrams of the hydrocarbon, 4.77 milligrams of that was hydrogen. So what's the rest? If we just subtract that from the original, we now have the mass of hydrogen and the mass of carbon. Now, we can take those two masses and find how many moles of each compound and get the mole ratio to get the empirical formula. So that's what we're going to do right here. The 42.8 carbon, 1 mole of carbon is 12 grams. Hydrogen, 4.77, 1 mole of hydrogen is 1.01, so that we get 3.56 moles of carbon and 4.72 moles of hydrogen. Well, actually, we have millimoles, but all we're looking for is the ratio. And so as long as our units are the same, the ratio will be, we can get it into a 1 to something ratio by dividing each of these by the smallest. So the smallest is 3.56. 3.56 divided by 3.56 gives us 1, but 4.72 divided by 3.56 gives us something that's decidedly not a whole number. So how do we get 1.33? What can we multiply that by to get it into a whole number. So we're looking for some small factor. In this case, we see that we can use 3, so that 1.33 times 3 equals 4. So now we have a whole number. Of course, we have to multiply both elements by that small factor. And so here we have 1 times 3 is 3. So now we have our empirical formula of 3 to 4, 3 carbons for every 4 hydrogens. So we can now write the molar mass. 3 carbons for every 4. Let's try that again. We can now write the empirical formula of 3 carbons for every 4 hydrogens. And that goes on to give us the molar mass of 40 grams per mole. 40 grams per mole is the molar mass of the empirical formula. And we were told that our molecular formula was somewhere between 115 and 125. So I've used a molar mass of about 120. Now, I can see that if I divide 120 by 40.0, that I'm going to get 3. So 40 times 3 is 120, my molar mass that was given. So that means if I take my empirical formula and multiply it by that same factor, I'm going to get my molecular formula. So now I have both the empirical and molecular formulas of this compound.